A design pattern is a general, reusable solution to a commonly occurring problem within a given context in software design. You can look at it as a template you can use to solve common issues you will encounter during software design. They help with creating flexible, easily maintainable applications. In that regard, you can consider them best practice approaches to common problems. Very important to remember is that you should see these patterns as a template to start from and not as a rule set in stone. Implementing a pattern can typically be done in multiple ways, depending on, for example, the language you're implementing them in. A good example is that you'll notice a lot of patterns talk about abstract classes. However, in C# you can often use an interface instead, if all you need is a contract and not an implementation to start from. Throughout the course, you will learn how to implement these patterns in various ways. That being said, each pattern has an intent. For example, the adapter pattern, which we'll encounter, intends to let classes work together that otherwise cannot. No matter how you implement this pattern, the intent should remain the same, and that is true for all patterns. A lot of these patterns are so common that you've undoubtedly used them before, maybe even without knowing that you were using them. Important is that you shouldn't learn the pattern implementation from the top of your head. Instead, learn which problem a pattern solves. The patterns we will cover in this course are the well-known Gang of Four design patterns. The Gang of Four are Eric Gama, Richard Helm, Ralph Johnson, and John Vlissides. In 1994, a long time ago, these guys published a book that, to this day, is the de facto standard work on software design patterns. Design patterns, elements of reusable object-oriented software. It consists of 23 patterns. Those are the ones we will cover in this course. Even though the book was written in 1994, these patterns are still commonly used today. They are often built into the framework we use, so we use them without knowing it. They all solve common issues you might encounter when designing, in this case, object-oriented software. A few examples of problems that are solved by them are: how do I ensure that only a single instance of a class exists? How do I make two objects with a different interface work together? How can I extend an object's interface without changing the underlying object? How do I enable support for undo functionality? And many, many more. That being said, the book was written in 1994. If you read through it, you'll quickly notice that it's not always easy to map the implementation you can see in the book, which is C++ 2.0, to a commonly used language from 2022, like C#10. It wouldn't even be that easy to map it onto the current version of C++, which is version 20. Or at least you wouldn't be using modern features of that language. So, even though I will cover all 23 Gang of Four design patterns in this course, and I'm basing myself on the book, it's definitely not just going to be a copy of the examples from the book. The pattern implementations will be adjusted to modern-day possibilities, using current real-life examples you might encounter in your day-to-day life as a developer. The intent will, of course, remain the same. As far as some of the use cases, consequences, and related patterns are concerned, not everything from the book is current today, and some consequences or use cases that are common today weren't at the time the book was written. Where applicable, these will be adjusted. This is very much a current course and not a 1994 course. I mentioned before that it's not that important to learn the exact implementation of these patterns from the top of your head. Instead, learn which problem they solve. And the problem they solve, that relates to the type of the pattern. The Gang of Four define 3 types of patterns. Let's check those out next. The first pattern type is the creational pattern type. It consists of patterns which all deal with object creation. The idea behind these patterns is to abstract the object instantiation process. In other words, these patterns will help with making your system independent of how its objects are created, composed, and represented. if you notice you've got a lot of new statements in your client code and tightly coupled classes using concrete implementations, these patterns will help with that. In fact, almost all patterns help with enabling loose coupling throughout your codebase. The second pattern type is the structural pattern type. This one consists of 7 patterns. They all deal with ways to define relations between classes or objects. In other words, they are concerned with how classes and objects are composed to form larger structures, hence the name. Lastly, the third pattern type is the behavioral pattern type. There's 11 of them. These types of patterns define ways to communicate between classes or objects. They characterize complex control flow that's difficult to follow at runtime, and they let you concentrate on the way objects are interconnected. Let's have a look at 2 important object-oriented principles you will encounter throughout the course. There's 2 important object-oriented principles that are followed by the Gang of 4 in their design patterns. The first one is program to an interface and not an implementation. The second one is favor object composition over class inheritance. You will see these 2 principles coming back throughout the course in a lot of patterns. Let's start with the first one, program to an interface, not an implementation. This has 2 main benefits. 1. Clients remain unaware of the specific types of objects they use, at least as long as the objects adhere to the interface that clients expect. And 2. Clients remain unaware of the classes that implement these objects. Clients only know about the interface. Let's clarify this with an example. What you see on screen here is a very typical example of this. We've got an interface, iDiscount service, and 2 implementations, Belgium discount service and France discount service. Then there's a class, client, that requires a discount service. In our example, it gets that through constructor injection, but that's not really important for the example. Important is that the client doesn't rely on Belgium discount service or France discount service. It relies on iDiscount service, the interface, not the concrete implementation. And that is what allows loose coupling. What you have to keep in mind, though, is that the book was written in 1994. A language like C# didn't even exist at that time. When we, these days, think about program to an interface and not an implementation, we will quickly think about the interface language feature, just as I've shown in the code sample. However, what the Gang of 4 is talking about is not a technical interface language feature defined with the interface keyword. They are talking about the set of requests that an object can respond to, which is the object's type. Now, of course, there is a close relation to the interface language feature we know about, as it can be implemented as such, but you can also implement the interface they're talking about with an abstract class. It is important to remember that distinction. I mentioned before that these patterns can be implemented in various ways, using the language feature interface versus the language feature abstract class is one of the main ways that leads to different implementations. On screen, you see the example we just detailed, but implemented with an abstract class. Most patterns that talk about the object interface or an interface can, in C#, be implemented with abstract classes or interfaces. Throughout the course, I will use both. To decide on which to use, a good rule of thumb is use an abstract class to create functionality that subclasses can implement or override. And use an interface when all you need to do is define functionality and not implement it. And whereas a class can extend only one abstract class, it can take advantage of multiple interfaces. When a pattern starts working with interfaces, as defined by this principle, you will notice that we'll often start adhering to the open-closed principle from the solid coding principles. That's the principle that states that software entities like classes, modules, and functions should be open for extension but closed for modification. When that is the case for a certain pattern, we will look into it. On to the second principle. That was favor object composition, over class inheritance. Let's clarify these two terms. Both are techniques for reusing functionality in object-oriented systems. Class inheritance lets you define the implementation of one class in terms of another's. You simply create a subclass of a base or parent class. Both terms are used interchangeably. And you do that by inheriting the parent class. Like that, you are reusing functionality of the parent class in your subclass or derived class, however you prefer to call it. This is often referred to as white box reuse, meaning that the internals of parent classes are often visible to subclasses. And then there's object composition. Here, new functionality is obtained by assembling or composing objects to get more complex functionality. This requires that the objects being composed have well-defined interfaces. It's referred to as black box reuse, because internal details of objects are not visible to the composing class. Both have their advantages and disadvantages, and the debate can get quite heated. This isn't an OO primer course, so I'm not going to get into that discussion. Moreover, in almost any system, both techniques are commonly used. What's important for this course is that these patterns will, wherever possible, favor object composition over class inheritance, as the Gang of Four felt that inheritance as a reuse technique is overused. And when you see some systems that regularly define classes that inherit from each other 6 or 7 levels deep, I tend to agree. That is not a great design. Designs are often made more reusable and simpler by relying on object composition. And that's a good thing, because unnecessary complexity is something you should definitely avoid. When a pattern starts working with composition as is defined by this principle, you will notice that we will often start adhering to the single responsibility principle from the solid coding principles. That's the principle that states that a class should have one and only one reason to change. In other words, one responsibility. When that's the case for a certain pattern, we will look into it. And with that, it's time for this module summary. A design pattern is a general, reusable solution to a commonly occurring problem within a given context in software design. You can look at it as a template you can use to solve common issues you will encounter during software design. They help with creating flexible and easily maintainable applications. In that regard, you can consider them best practice approaches to common problems. The patterns we will cover in this course are the Gang of Four patterns. 23 object-oriented patterns that are still commonly used today. There's 3 categories. Creational patterns help with making your system independent of how its objects are created, composed, and represented. Structural patterns are concerned with how classes and objects are composed to form larger structures. And behavioral patterns characterize complex control flow that's difficult to follow at runtime. They let you concentrate on the way objects are interconnected. 2 principles you'll have to keep in the back of your mind throughout the course, as the patterns are built with and around them, are to program to an interface and not an implementation, and to favor object composition over class inheritance. We just looked into those in detail. That's it for this module. Up next, the singleton pattern, a very common one and an easy one, ideal to get used to what a design pattern is.